Okay, by the definition here, especially I power 4 equal to 1 is there. What is the element? Here I be the element given in this group. Therefore, order of I equals to 4. That implies I power 4 equal to 1. Therefore, 1 be its multiplicative identity. And here 4 being the least positive integer here. Okay. At the same time, minus 1. So, therefore, this is the element of order. One order is 1. Minus 1 order is 2. And at the same time, I order O of I equal to 4. Therefore, I power 4 equal to 1. Therefore, I an element 6 order is 4. And at the same time, minus I whole power 4 equal to 1. That's why minus I an element of the order is 4 is there. Therefore, now this is the very important concept. 1 minus 1, I minus I. Now, these are all elements, especially for an imaginary of 4 roots of unity, and here hence their orders are 1 order is 1, minus 1 order is 2, I order is 4, and minus I order is 4 is there. Okay. Now, particularly, just you have to see the one of the relation. Group order is 4 because there are number of elements is 4 given in this group. Therefore, cardinality of the group is 4. Particularly, we have to mention here the elements of the order is 1, 2, 4, 4. Comparing it with both. Okay, 1 less than 4, 2 less than 4 because these are all elements. This is A1, A2, A3, A4. First element order is less than group order. Second element of the order is this is 2. That is also less than 4. Third element order, I element of the order is 4 because I power 4 equal to 1. That's why this element order is always less than or equal to group of the order. And the last element minus I, this element order is also 4. Therefore, 4 equals to 4. Now comparing it both their orders, element of the order either less than or equal. Now that is one of the example. Now this is particularly just you have to see here. This is particularly very important example. Now there are so many times repeated here. That is imaginary of 4 roots of unity. Now the cube roots of unity. There are 2 important examples well established in algebraic concept. Now that is here capital G. This is also cube roots of unity elements 1 omega square. Here this is the find the order of elements for the cube roots of unity. Okay. And how to guess the relation? Element of the order is always less than or equal to the group of the order. Now these are all elements A1, A2, A3. 1. We are taking the 1 first element A1 equals to 1. Then its order of 1 is always 1 because 1 power 1 equal to 1. This is the least positive integer. What is the second element? Omega. Order of omega. What about the relation in omega? Omega cube equal to 1 because that's why the integral power is 3 is there. That is omega cube equal to 1. So order of omega equal to 3. Next, third element omega square. Omega square whole cube equals to, that is omega power 6. Okay, omega power 6 can also be written as omega cube into omega cube. So 1 into 1 equals to 1. So when it is omega square, just we have to apply the integral power element is 3. Now we are given the result is identity. So that is omega power 6 equals to 1. So that's why omega square element of the order is, this is the integral power, that is the 3. That is the order of omega square. So finally, we are getting their orders 1 omega square are, here are 1, 3, 3. Now these orders, comparing it with the group of cardinality of the group. Now this it read as cardinality of the group and order of the group. That's enough. Now 1 equals to 1 less than 3, 3 equals to 3, 3 equals to 3. So these are all elements. Now comparing it with the group, a group of the elements, group of the order or cardinality of the group. So finally, order of A less than or equal to the order of the group. That's why now these are all examples. Now at the same time, just you have to see here already. We have to explain the one of the modular relation is there. What is the modular relation? Now see this one. This is the modular relation. Okay. Now here composition is addition modulo 5. Find the orders. Please stand here. Find the orders of of in additive group under addition modulo 5 to form an abelian group that is capital G equal to set of 0, 1, 2, 3, 4. That is the addition modulo 5 elements. Okay. What is the order of 0? Now these are all elements in this group. Capital G equal to 0, 1, 2, 3, 4. Under addition modulo 5 of the elements is 0, 1, 2, 3, 4. Okay. Now 0 when it is, what is the additive identity? Additive identity is 0. That's why 0 is when it is 0. Now 0 is 0 of R3 is 0. That's enough. One order. How many times applying in the integral power? Order of 1 equal to 5 times adding. Now we are getting the 0 is here. 5 times means 1 plus 1 plus 1 plus 1 plus 1. There are 5 times. 1 plus 1 plus 1 plus 1 plus 1 is that is the 5. 5 divides 5. Remainder is 0. So order of 1 equal to 5. There are order of 0 equal to 0. Now here that's enough. Order of 2 equal to 2. How many times dividing with how many times you are taking 2? 2 plus 2 4. 4 does not divide 5. 2 plus 2 plus 2 6. 6 does not divide 5. Okay. And 5 does not divide it by 5. 6 is does not divide it by 5. Okay. And again 3 times 3. 2 plus 2 plus 2 6. 4 times 2 plus 2 plus 2 plus 2 8. And again 2 we are taking the 5 times is here 2 plus 2 plus 2 plus 2 plus 2. 5 times you are taking, then it adding with the result is 10. 10 divided by 5 is there. So we are taking the 2, only 5 times is here. Now that's why here the element is, okay, order of 2 is also 5 is there. 3 is also taking here. 3 plus 3. Okay, that is also 5. 3 plus 3, 6. 6 plus 3 is 9. Okay, 9 plus 3 is 12. Okay, 12 plus 3 is 15. How many times are taking? Now that is also 5 times. So especially just you have to take it when it is divided by 5, we are getting the value is 0. Now number of times is the number of times taking the positive integer. That positive integer, how many times are taking is divided by 5. Now that is the then it's a order. Now therefore just you have to particularly see here 4 is also taking 5 times. 4 plus 4. That is 8. 8 plus 4 is 12. 12 is also does not divided by 5. Okay. 12 plus 4, 16. 16 is also does not divided by 5. Now 16 plus 4, 20. So 5 times you are taking the 4. When now all the values are adding, then it is divided by the modulation of the value is 5. Therefore, 5 times you have to take it. Now then the result is identity. We are getting the identity element. Then it's the order. Now this is the special binary operation. Now that's enough. This is also one of the important concept. And just you have to see this theorem. What is the theorem? What is this theorem? Just you have to see here. And according to this, there are so many examples order of an element with respect to the composition. Now, how to prove the order of an element of a finite group is finite and is less than or are equal to the order of the group. Suppose, first of all, now in examination, this type of question is given. Define order of an element of a group. Prove that order of an element of a finite group is finite and is less than or equal to the order of the group is there. Okay, that's enough. Just you have to see here. Okay, now according to this one, then just you have to see that. First of all, you have to mention the definition of an order of an element of a group. Now, just to prove that order of an element of a finite group is finite and is less than or equal to the order of the group. Now, in the remaining 4 classes, we will discuss entire this PDF. In this PDF, especially, there are so many important theorems, especially in group theory and rings and fields. Already, this PDF already have dispatched through WhatsApp is there. Now, just already recently, 2 days back, and first day is also posted, especially in this PDF. Now, this theorem is by the similar, the continuing process, first of all, so we will discuss the theorem is order of an element of a finite group is finite and is less than or equal to the order of the group. First of all, then its proof is just you have to see here G under multiplication be a finite group. And given this group, we are taking the element is A. By closer exam, group of the elements is A into A square, A into A square, A cube. A into A cube is A power 4. And continuing in the same manner, we are getting the closer elements given in this group. Okay. When the group is finite means now given the particular elements, now all elements are different and distinct. Now suppose that's why when the group is finite, all the positive integral powers of A is there. Those positive integral powers of an element A is A square, A cube, so on. Now these elements cannot be distinct. Okay. Now in this in between A power R and A power S, there are two elements. Those elements are different and distinct. Suppose here R and S, those elements are being the integral power of the elements because R and S both are natural numbers. That's why hence their integral power of the relation is R is always greater than S is there. Suppose A square 2 is less than 3. Okay, 2 is less than 3. 3 is less than 4. And in the same manner here R and S both are being natural numbers. Suppose here R is greater than S, A power R equal to A power S is there. Suppose we are giving the in between their elements, then the distinct elements A power R, when those elements are equal, if it is equal, A power R equal to A power S. Now applying on both sides, A power minus S is there. That is A power R into A power minus S equal to A power S into A power minus S. Now here that is A power R into A power minus S is A power R minus S equal to A power S into A power minus S is A power 0 because that value is identity. This is A power 0 equal to identity. Therefore, here put R minus S equal to M is there. That is A power M equal to identity. Since when it is R is greater than S, here M being a positive integer. Suppose there is a positive integer, M being a positive integer such that A power M equal to E is there. Suppose when it is M is the least positive integral value of M such that A power N equal to E is there. Now this condition is completely, now what is the meaning of this one? An element of the order is equals to N is there. Now by this condition, element of the order is N. Just you have to mention here. Suppose N is N when it is must be a finite, element of order is also finite. That's enough. So given this theorem, just you have to observe here already we have derived, we must derive here. Therefore, order of an element of a finite group is finite. When the group must be a finite, so element of the order is also finite. In the group of the elements that is denoted by A, all the elements of the closure of the elements is A square, A cube, and so on, A power R and A power S and so on, A power N. So all the elements are denoted by, suppose you are taking the element is A belongs to G, therefore then its order is also finite is there. Okay, there is no doubt. Now when the group must be a finite, just we have to explain its order. Now that order is least positive integer. That's enough. Now here to prove that element of the order is less than or equal to order of the group. Now that is one of the important condition. Now this is our proof is there. Derivative. We will derive here. We will prove that order of A less than or equal to order of G. Element of order is always less than or equal to the order of the group. There are already we have explained the previous examples. Just we have to imagine the 4 roots of unity and cube roots of unity and special binary operation 8/5. Now just you have to see here. There are so many examples. We have to understand to find an elements of the order. Okay. Now, if possible, suppose this is an order of element less than or equal to order of G. First of all, if it is possible, element of the order is greater than. This is the contradiction part. Element of the order is greater than order of G. That is the possible, our assumption. Suppose element of the order is N. What is the closure of the elements? A square, A cube, so on, A power N. These elements are also belongs to G. Any two elements are not equal. because here a power 2 or a square. So a square not equal to a cube. A cube not equal to a power 4. In the same manner, a power r is not equal to a power s. But if possible, a power r equal to a power s. What about the relation? Here r is greater than s. But here the r and s values both are lies between 1 and n is there. That is, this is the 1 and n. The integral power of the elements. Those integral power of the elements in between s and r. That is a power s and a power r. Both elements are equal. That is 1 less than or equal to s less than r. These elements are lies between 1 and n is there. Suppose applying a power minus s, now already we have derived here a power r minus s equal to e. That in the integral power is r minus s lies between 0 and n is there, because r greater than 0. Because an element of the order is always less than n here, which is a contradiction. Suppose in this above expression, order of a is greater than order of g. Order of g means n, the group of the order is n. So order of a is greater than n, we have to take n. But here especially, this is the contradiction part, because order we will we have to prove the here. We have to prove here order of a less than n. Hence it is a contradiction part. Now all the integral power of elements a square, so on, a power n. These elements are different and distinct elements of G. Therefore, n is greater than order of G. This is not possible. That's why order of A less than or equal to order of G. Okay. Hence, that is the proof. Okay. Now, very important theorem is here. Okay. That theorem is also very important. See the another one, because there are so many important theorems here. Okay. Just you have to see here. If H and K are two subgroups. Okay, this is the subgroups of this concept. Okay, please stay on the line. Because there is no, we are only very few classes. That's why according to the our concept, according to the understanding capacity here, now we will explain the some important theorems, and particularly entire remaining 3 classes. Okay. Just you have to see here. What is the theorem? If H and K are two subgroups, please stay on the line. H and K are two subgroups of a group capital G. What is the group? Let G be a group and H be a subgroup. And before that, what is the subgroup of this part? Subgroup means now any non-empty subset of a group to be a subgroup. Now, in seeing your textbook, just you have to see and refer. In your textbook concept is there. Please see and verify here. This is the second. Please stay on the line. What is that? Second unit or third? Group. Third unit is there. This is the subgroup concept. Okay. Now, just you have to see what is the subgroup. Let G under multiplication be a group and H be a non-empty subset of G. Non-empty subset means now already set is there and one of the subset is there. Subset means some few elements given in the set. Just you have to write down some other few sets. Now those sets are completely depends upon the given the set. Now that is non-empty subset of G means now there are some of the few subsets through the given the group. Okay. Now with respect to the same operation, that is also must be repeated in the same expression given in H. G under multiplication be a group. Now according to the group, we have to construct a non-empty subset is denoted by capital H. Now it reveals the same operation in capital H. Therefore, H under multiplication to be a subgroup means same postulates in the group, same postulates with respect to the non-empty subset of H in G. All the postulates must be held in capital G. H is in capital G. Those non-empty subset with respect to the operation to satisfy all the axioms of a group that is called a subgroup is there. Therefore, here H under multiplication is a subset or equal to G under multiplication. That is also one of the subgroup. Okay, here H under multiplication be a subgroup. Now that subgroup means a subgroup that is also non-empty subset of a group. All the postulates with respect to the operation. With respect to the operation, all the postulates must be satisfied. All the conditions are satisfied. Non-empty subset of the elements of a group that is called a subgroup is there. Okay. Now suppose G under multiplication be a group itself. Here identity element is there. Only identity element given in this group that is called trivial subgroup of G. When the group itself and identity element must be involved. So that is only identity element given in this group. Now that type of subgroup is called trivial subgroup or improper subgroup of capital G. Okay, there are two types of subgroups, proper subgroups and improper subgroups. What are the improper? Improper means trivial subgroups. Okay. Second example, here the n is multiplying with the integers, n being any non-negative integer n such that n multiple of the integers, that is denoted by set of n into small a being any one of the integer, that is a belongs to z. Therefore, given this set, nz set is the set of na, such that here a being any integer. That is also a subgroup of z under addition. Z under addition be a subgroup. And what is the subgroup? Z under addition be a group, and subgroup is nz is also one of the subset, and those subsets of the elements is na1, na2, na3, so on. These are all nz is a subgroup of z under addition be a group. Okay. Now here third one, q under addition be a group. In the group of the elements are rational numbers. What are the subgroup of the elements? That is integers. In a group rational numbers, subgroup is integers under same operation. Suppose here addition be a one of the binary operation given in this group, and multiply and subgroup is also same binary operation, but not varies. Okay, it should not be varies here. Here addition be a one of the binary operation through the rational numbers, but in the subgroup of the elements are integers with respect to the same operation. Okay, therefore Q under addition is a subgroup of R under addition. Therefore, R under addition be a group, and subgroup of the elements are rational numbers under the same operation. Now these are all good examples of subgroups. Okay. Now suppose here capital G equal to 1 minus 1 I minus I. How to write the subgroup? 1 and minus 1, because 1 be the multiplicative of identity. Okay, this is also a 1 and minus 1 is also a one of the subset, and that subset must satisfy all the group axioms. Now all the group axioms means with respect to the same operation. That's why H equal to set of 1 minus 1 is a subgroup of capital G equal to 1 minus 1 I minus I, and 1 and I, 1 and minus I, because always you are taking with 1 is there, because without identity of any subset, we can't define the subgroups. Now, these examples are also verified in the last end of this unit. Okay. Now, just you have to say here, there are proper subgroups and improper subgroups. Let G be a group and H be a subgroup. H contains capital G. Means that is, H is called a H equals to when it must be identity, that is improper subgroups or trivial subgroups. Now that the element not equal to identity, that is the proper subgroup. That is H not equal to set of E, H not equal to G. So therefore, identity must be generated, contains capital H, contains capital G. Now this type of condition is called the proper subgroups. According to this condition, can also be written as generated E contains is a subset of H, and it is also a subset of capital G, or H is properly capital G. Now, there are so many types of our convenience. It read as generated E contains capital G, contains capital G. Okay. Now that is one of the important concept of proper subgroup. Only subgroups generated E and capital G. Now these two sets are called improper subgroups or trivial subgroups. This is the proper subgroup condition. Okay. Now there are so many examples here. Addition modulo 5. Okay. Already we have explained this example is in the previous part. What are the elementary properties of subgroups? Now this is one of the necessary and sufficient condition of a subgroup. Please see it very carefully. Just see and verify here. Elementary properties of subgroups. G under multiplication will be a group and H be a subset of G. When the group of a subgroup is denoted by capital H, if and only if, now the following conditions are true. First of all, H not equal to pi. Pi means H must be a non-empty. Now, with respect to the closure condition, A into B belongs to H. That is the closure condition under multiplication. A, B belongs to H. And next condition is A inverse belongs to H. This is the inverse of A is A inverse. Now, the same element given in the subgroup and then their inverse is also must be involved in H is there. That's why when these three conditions are satisfied, that is called a, then it is a subgroup of capital G. Okay, now this is one of the important, necessary and sufficient condition to be a subgroup H of capital G. What is the first necessary and sufficient condition? H not equal to pi. And second condition is A comma B belongs H, A into B belongs H. And third condition, A belongs H and A inverse belongs H. Now these theorems are just you have to see and refer in your textbook is there. Okay. Now this is the main preliminary part of subgroups to be a subgroup of capital G. Please share the line. Okay. Suppose capital H be a subgroup of G, then already when it is a subgroup, before that it is a group is there. H under multiplication is a group. Here multiplication is the one of the binary operation. Strictly now same binary operation in H is there. And according to that, when the group it is consisting some of the elements, automatically subset can also be written as H is also be a non-empty set, because non-empty set means it is consisting some of the elements. Now those elements just you have to take A comma B belongs H and AB belongs H. Then the closure condition must be satisfied. Okay. And the third condition, when the identity element to prove third condition is there. This is the third condition. When H is a subgroup of G and three conditions are satisfied, that is the necessary part. And using these three conditions to prove that H under multiplication is a group when it is a subgroup is there. Okay, the H under multiplication is a subgroup when it is a group. Okay, that is the sufficient part. First of all, given the conditions, those conditions are these three conditions here. H not equal to pi means it is consisting some of the elements. A comma B belongs H and AB belongs H. This is the closure condition. Okay. Now, inverse element completely based upon the identity property. That is the G3. G3 means when the identity element, same identity in the capital G, same that identity element is also in H is there. Because here E beats identity in H, choose AB any one of the element. A into A, E equal to E into A equal to A is there. By cancellation law, A equals to E equals to E dash is there. Okay, E equals to E dash. That is the left cancellation law. Okay. Alright, for any A belongs H, when the A belongs H, what is the inverse of A? A into A inverse equal to E. That is the inverse example. G4. Okay. Now, identity is also inverse element. It is completely depends upon the identity part with respect to the same binary operation. That's why A into A inverse equal to A inverse into A equals to identity is there. Therefore, here A dash or A inverse, whatever it is. This value is A inverse. So A into A inverse equal to E. Therefore, A inverse is the inverse of A. Therefore, every element must be expressed in capital H to find the inverses of given with respect to the same elements given in the non-empty subsets. Therefore, now here A inverse is also belongs to H. Therefore, these three conditions are satisfied. That is the necessary part. And second one, sufficient part is conversely. Means H satisfies, suppose H satisfies first condition, second condition, and third condition. These three conditions are satisfied. Okay. By second condition, that is the closer relation, H becomes a binary operation on H. When it is HB non-empty, here AB any one of the element given in this part, that is the capital H. Therefore, A inverse is also every element must be expressed the inverse element. Therefore, A belongs to H means A inverse is also belongs to H by third property, that is the identity part. Because A into A inverse equal to identity. Here E belongs to H. When the identity element in capital G, that is also in H, it becomes the identity in H. Same identity. When the group of the identity element, it repeats the same identity element in H is there. Okay. Now, you have here each and every element. Suppose A belongs to H. Every element must be expressed the inverse. Because A into A inverse is the identity is there. Therefore, A inverse is the inverse of A. Therefore, H is properly contained in capital G because itself of this part. So, same elements to satisfy the associative property, because closer condition verified, identity element is there, inverse element is there, and the remaining the postulate is associative. Therefore, when it is the closer relation, then automatically it satisfies the associative part. Therefore, H under multiplication is here. All the postulates satisfied, that is called a group. Now, given the non-empty subset of the elements, to satisfy all the postulates of a group, therefore H under multiplication is a group is there. Therefore, finally H is a subgroup of G under multiplication. That's enough. Okay. Now this theorem is very, very important in examination. That is the one of the non-empty subset of a group to be a subgroup. What is that? Here H not equal to pi and A comma B belongs to H, A B inverse belongs to H. Very important, students. Listen carefully. Now this theorem is very important. Now strongly we believed that is the subgroup of this part. Okay, because here let G under multiplication be a group and H be a subset of G. Now this is the proper statement is there. G under multiplication be a group and same binary operation in H. Therefore H be a subset of G. When the subset must be a subgroup, and to prove that these two conditions, H not equal to pi and A comma B belongs to H and AB inverse belongs to H. And at the same time, according to using these two conditions to verify H under multiplication is a group, then automatically then it is a subgroup is there. That is the sufficient part. That's enough. And alternatively, in examination, this type of question is also given. What is that? A necessary and a sufficient condition for any non-empty subset of capital H of a group capital G to be a subgroup. A belongs to H, B belongs to H, AB inverse belongs to H. Here B means B inverse is the inverse of B in capital G. Now this is also another one of the part, another way. This is the second approachment of the statement, giving the statement. Okay, either this one prove that this one, or prove that a necessary and sufficient condition for a non-empty subset H of a group capital G to be a subgroup is that A belongs to H, B belongs to H, AB inverse belongs to H. Now this is the another way of the statement. Suppose first of all H is a subgroup of G. Already directly it is a subgroup. Now already it is a subgroup means before that it is a group is there. Okay, by the condition, the first theorem by the condition, what is the second and third one? When the closer condition and the inverse element is there, and according to this one, you have to construct the relation is A comma B belongs to H. Here B means non-zero element. The non-zero element means inverse element must possess. Multiplicative inverse is there. Now, therefore, A belongs to H. B not equal to 0 or 0 not equal to B belongs to H means inverse element must be possessed. Therefore, A belongs to H, B inverse belongs to H. Then the closer condition is A, B inverse belongs to H. Now that is the necessary part. This is the necessary part. Directly, condition is applied. Condition is there. Now here the conversely part. Just you have to see the converse. This is the sufficient part. Just you have to observe this one. Enter in algebra. Prove that a necessary and sufficient condition means that is the if and only if means that is the necessary and sufficient condition. One implies A implies B, B implies A. Means the second one is using those conditions. Using these conditions, 1 and 2 conditions, to prove that H is a group. H under multiplication is a group. Automatically, then it is a subgroup is there. Okay. Now, using these two conditions, given the conditions, H not equal to 5 means at least one element is there. A belongs H. Okay. A belongs H means A must be non-zero element if its inverse exists. Therefore, A inverse belongs H. Now, A belongs H, A inverse belongs H. What about the condition? Using this condition, if B equal to A inverse is there, or A into B means A into A inverse belongs H, identity element is there. Because inverse completely based on the identity part. Therefore, identity element in H is there. Therefore, A belongs H, E belongs H. What about that? E belongs H, A belongs H. Means now using this condition, E belongs H, A belongs H means this is E into A inverse belongs H. Therefore, every element to express the inverse element is there. Now, finally, last but not least, now this condition is also verified here. A comma B belongs H, and A comma B must be the non-zero element. Therefore, B inverse belongs H. Now, A and replaced B by B inverse in the above condition, second condition. Therefore, B inverse whole inverse. Therefore, clausal condition is also verified here. A B belongs H. All the postulates must be verified through the using these two conditions. Therefore, by the first theorem, by the first and the necessary subject part of a subgroup, therefore H under multiplication be a group is a group, and then automatically it satisfies the conditions. H under multiplication is a subgroup of G under multiplication. Now, this theorem is very important. Students, listen carefully and look at observe here. This is the multiplication as the composition. Now, especially in this manner, we have to take the under addition. Addition is the one of the operation. Now, how to write the necessary and sufficient condition? A belongs H, B belongs H. Under addition as the composition. What is the additive inverse? Subtraction. Therefore, B not equal to 0 under addition means minus B belongs H. Therefore, A minus B belongs H. And comparing it with the above theorem. Just you have to write the. It is just you have to prove that as an individual effort by the second theorem to prove that this note. Okay. Now A belongs H and B belongs H and A minus B belongs H is there. Okay. Now same in the same manner. There is no doubt. Okay. Necessary and sufficient condition for a non-empty subset H of a group capital G to be a subgroup. A belongs H and B belongs H and addition as the composition. A minus B belongs H. Okay, here minus B is the inverse of B in G. Now we have to practice. This is our practice purpose. H under H is a subgroup of G. By second and third condition of first theorem, A comma B belongs H, A comma minus B belongs H, A minus B belongs H. That is the necessary part. Sufficient part is conversely. Suppose that H satisfies first and second condition is there. Therefore, H not equal to 5 and we can choose A belongs H, minus A belongs H. A minus A means that is the 0 because the additive identity element is 0. So that is denoted by E belongs H. Okay, A belongs H and 0 into means E into A inverse. E into minus A belongs H. Therefore, minus A is also belongs to H. That is the clausal condition with respect to the additive identity. And A comma B belongs H, A minus B belongs H, A minus B and its inverse. Okay, inverse of minus B means minus of minus B. That is A plus B belongs to H. That is clausal condition is satisfied with respect to the additive composition as the one of the binary operation. That's why by second and third conditions in the first theorem, we already proved that here H under addition is a subgroup of G under addition by this individual effort of this one is according to this note. Now we have to practice this theorem in the above manner. Now directly we must derive the closure condition to express the subgroup of this part. A into B belongs H. Suppose G under multiplication be a group, H be a non-empty finite subset of G. H is a subgroup of G if and only if A comma B belongs H. By the closure condition, directly we have to mention the necessary and sufficient condition of to be a subgroup is there. A into B belongs H. That is the closure condition. Now, see here, H is a subset of G. clearly condition is satisfied. Conversely, suppose that H satisfies the condition A comma B belongs H, A B belongs H. We shall prove that A belongs H and A inverse belongs H. Because here A belongs H means when the H must be a finite, directly condition is satisfied. That is the necessary part. When the closure condition is satisfied, that is the necessary part. Sufficient part is by this condition we must prove that H under multiplication is a group and it is a subgroup is there. Suppose any one of the element, now we have to find out the inverse of the element in H is there. A belongs H. When it is H must be a finite, means we are taking the n distinct elements. Now these elements are different and distinct. Okay. Now suppose AI element is there. A belongs H, AI belongs H, A into AI is also belongs to H. Now another element is in between AA1, AA2, AI, AAJ. Any two elements are equal, that is AI equal to AJ by cancellation laws, by left cancellation law. So set of these elements are n elements with respect to the closure of the elements of closure of H. Hence the distinct elements is AA1, AA2, so on, AAN. Now these are all n elements, elements of the subset of H. Now it is exactly n elements. In the same manner, now it is particular I equal to A is there. Suppose A belongs to H. Okay. Now here AI, what is the AI? A equal to AI means when AI must be the identity is there. A into E equal to A is there. Therefore AI equal to E is there. So identity element is also belongs to H. In the same manner, AJ equals to E. Therefore AJ is also means A inverse equal to AJ. Therefore AA inverse equal to E is there. Therefore A belongs H and A inverse belongs H. All the conditions, identity, inverse, all the postulates are satisfied by the first theorem. H under multiplication is a subgroup of G. That's enough. Now this is the one of the important concept is there. Now just we have to observe here. Now these theorems are very important. 3.3.4. Okay, let G be a group and any subgroup of G, it contains the same identity element of G. Already we have proved here. In the group of the elements, when it is the identity is there, same identity element is in this group. Okay, suppose H be a subgroup of a group capital G, E be the identity element of G. When it is H must be non-empty is there, that any one of the element is A belongs to H. Means A means a non-zero element means A inverse is also belongs to H. What is the closure condition? A into A inverse, then it must be identity. Same identity element in H, therefore E belongs to H by the improper subgroup of this part. Okay. Now, in the group of the identity element and subgroup of the identity element both are same, because without identity we cannot form the group of this part. Now, group is also according to the group we must construct some subsets, and those subsets to form a group is there. And those subsets to, when it is the subsets of form of the group with respect to the operation, now that is a subgroup of the formation. Okay, there are number of subgroups are there. Now this is the properties of algebras. Students, this theorem is so many times repeated in your examination. Listen carefully. Now this is very important part. Okay, please stay on the line. Okay. What is that seen here? What is the algebraic symbols? Algebraic operations are Boolean operations, union and intersection. So that's why these properties are algebraic properties and algebra of subgroups. Algebra of subgroup means now in the set theory, union and intersection are also well defined. Now those operations are in set theory and Boolean theory especially. Okay. Now these symbols are Boolean symbols. So Boolean expressions are also performed, especially in the set theory concept. So that's why union and intersection, there are two important operations in the set theory in the same manner, that is also Boolean theory. Okay. Now the intersection of any two subgroups. Who means there are any two subgroups are there. H1, H2. There are two subgroups of capital G. In between the operation is H1 intersection H2 is also a subgroup. Okay, it's very important. the intersection of any two subgroups of a group capital G, it is again a subgroup of G. Students, this is not by heart concept. Now, for the, especially in the continuing theory, the continuing part of subject, there is no single doubt. There is no doubt. At least any one of the theorem is there. These theorems are not by heart here. According to the subject concept, now easily to understood, and you must mention the automatically. Then you have to write the groups are also as an individual effort. Okay. The intersection of any two subgroups of a group capital G is again a subgroup of G. First of all, this is the group is there. In the square region is there. This is the group of this part, and there are two subgroups, H1, H2. Therefore, intersection of the symbols, when intersection of the Venn diagram is there, H1 and H2. And in between the both are common part is called H1 intersection of H2 is there. Okay. Therefore, H1 intersection H2 is a subgroup is there. Suppose H and K be subgroups of a group capital G. Let G be a group. H and K, there are two subgroups, or H1, H2, whatever it is, there is no problem. Same identity elements in the subgroups. G be in the group of the identities small e. Same identity element in H and in K. E belongs H, E belongs K. So at least one identity element is there. Therefore, H intersection K not equal to pi. Means some identity element is there. E belongs to H intersection K. Same identity element in H and K. Now we must mention the E belongs H intersection K. Therefore, that's why H intersection K not equal to pi, and it is also subset of capital G. Suppose any two elements in H intersection K, that is A is one of the element H intersection K, B is also another element of H intersection K. Therefore, A comma B belongs H, and intersection represented as and. That is the conjunction of this part. Okay, that is the statement symbol. Okay, A comma B belongs H. Intersection means same elements are also in the K is there. Suppose A comma B belongs H. What is the one-step condition? Now, second theorem is one-step test. First theorem is a two-step test. A B belongs H, A inverse belongs H. That is the two-step test. Write the two-step test of a subgroup. Means A B belongs H, A inverse belongs H. One-step test is A B inverse belongs H. This is the second theorem of necessary and sufficient condition of a subgroup. That is the direct condition. Using this condition, A B inverse belongs H. And according to this one, A B inverse belongs K. Therefore, H and K both are subgroups. Therefore, same element in H and K. That's why A B inverse belongs H intersection K is there. That's why by second theorem, automatically we have to prove we must derive here A B inverse belongs. This is entire this part is capital X is there. Therefore, capital X is a subgroup of G. Here, capital X equal to H intersection K is there. Therefore, H intersection K is a subgroup of capital G is there. Okay. Now, in the same manner, now one of the theorem is there. What is the extended part? Only two subgroups are there. There are a number of subgroups. Means that is the arbitrary family. In arbitrary intersection of family of subgroups is a subgroup. That is intersection I belongs to H. Okay, HI. Or intersection of HI represented as I belongs to capital I being it index of the set. That is H1 intersection, H2 intersection, H3 intersection, so on. Enter the parties denoted by capital X equal to or capital H equal to intersection I belongs to capital I or I belongs delta of HI. That is the arbitrary intersection to be a subgroup. So, okay. Now that's it. Now that is also same manner. A B inverse A comma B belongs HI and A B inverse belongs HI is there. Suppose A comma B belongs H1 intersection, H2 intersection, H3 intersection, so on. Enter the parties denoted by HI is there. Here, particularly, you have to mention the two subgroups. But A B inverse belongs HI. That's why A B inverse belongs. What is that? Capital H. Capital H equal to arbitrary family of the subgroup. That is capital H equal to set of intersection of HI. It is simply intersection small t belongs capital T of HT. Intersection small I belongs capital I of HI. That is also a subgroup. The intersection of an arbitrary family of subgroups is to be a subgroup. Now, particularly this theorem referred as the union of any two subgroups. It is very important. Each and every point, just you have to understand here. Now, these theorems are very important in the final examination because these two theorems combining, there are so many times repeated in the final examination, prove that the intersection of any two subgroups is to be a subgroup and union of any two subgroups to be a subgroup if and only if one is contained in the other. This theorem can also be written as the union of any two subgroups to be a subgroup if and only if one is contained in the other. This theorem is also another statement as to be expressed as the union of any two subgroups to be a subgroup if and only if one is contained in the other. That's enough. Now that is in the words H and K be any two subgroups. Union of the subgroup means H union K. This is also one of the binary operation or Boolean symbol or a set of the symbol. H union K B is a subgroup of G. Now, if and only either H contained are equal to K, K contained are equal to H. That's enough. Now, there is one is contained in the other of this part because algebra. Now, it is completely one of the beautiful expression, especially in this universal part. This is already derived theory. That is not the story. Okay, algebra is not a story. Now, there is also a completely derived part. Now, here in the latest version, latest technology, in the infrastructure of IT structure, it is completely IT infrastructure is also completely based upon the algebraic concepts. Okay, there is no doubt because it is proved theory part. Okay, what is the use of algebra means enter the nowadays we have to achieve that there are so many competitive examinations. Now, also this is also one of the research content theory is also there. There are modern algebra, means abstract algebra or linear algebra, Boolean algebra, lattice algebra. So there are so many types. Or the finite structural group theory is also derived here. Okay, algebra can be derived at a 22nd stage in the universal part. Okay, there is no doubt. Okay, now see this here. This theorem union of any two subgroups H contained are equal to K, H is subset are equal to K, K subset are equal to H. Therefore, H union K are represented as union H union K, either K or H. So both are equal here. H union K is an equivalent to either K or H. Therefore, already here it is given here the preliminary part is H union K is a subgroup of G. This is the necessary part. That's enough. Now, either H is depends upon the K or K depends upon H. And before that, H is a subgroup and K is a subgroup. And union of the subgroup H union K is the primary part is a subgroup is there. Therefore, that's why H union K is a subgroup of G. Conversely, first of all, here H union K is a subgroup of G. You have to prove that H contained are equal to one is contained in the other. Either H contained are equal to K or K contained are equal to H. First of all, you have to assume that H does not contain are equal to K. We shall prove that K contained are equal to H. We shall prove that. But H not equal to contained are equal to K means A be any one of the element in H, but not in K is there. And another element B belongs to K, but B is not in H. That is the derived part. Suppose A comma B belongs H union K, means A belongs H and AB is also belongs to H union K. Either AB belongs to H or R. This is the statement it read as now statement of the compound part is also what is that? This is referred as or R. AB belongs H or AB belongs K. Now here AB any one of the element given in H that must be the non-zero element means the inverse element is also there. Therefore A inverse belongs H and AB belongs H. What about the associative? A inverse of AB belongs to H. By the associative part, A inverse A of B belongs H. A inverse A means identity. EB belongs H. Therefore, B belongs H is there. Therefore, here, just you have to observe here, A belongs H, but not in K. B belongs K, means B not equal to H. But here, B belongs to H is there. Therefore, same element in H, and that element is also K of the K is also contained are equal to H because B is in K is also there. Therefore, K contained are equal to H is there. Therefore, finally, H content are equal to K or R, K content are equal to H. Or K content are equal to H is there. Suppose K does not content are equal to H, we must derive here, we must prove that H content are equal to K is there. Therefore, that's why one is contained in the that's enough. That is the from the union of the subgroups. Now, this is very important theorem in especially those subgroups. Okay, students, already our time is over. If you are interested, now we have to continue here. There is no doubt. Okay, just here, just only 5 minutes is there. Okay, because later now the recording is also commencing in the late session. After 10 minutes is also recorded here. Okay. Now just you have to see this one of the theorem. That is the product of any two subgroups is also a subgroup. Now that is the theorem. Now this theorem is also very important in the short notes or whatever it is. That is also essay is there. There are two subgroups of a group capital G. Product of the subgroup is denoted by HK. HK means A belongs to H and A belongs to H and B belongs to K. What is the product? AB element. Product of the element is AB. Here A belongs to H and B belongs to K. So this is the product of the set. So the product of any two subgroups is a subgroup if and only HK equal to KH. This theorem is also very important. See here, these theorems are very, very important, and this is especially very most important. Okay, there is no doubt. HK is a subgroup of G, means just you have to assume any one of the element. That is, that element is say X. Suppose XB any non-zero element is there, then their inverse is also in the product of the subgroups. So here A belongs H, B belongs K. That product of the element of the subgroup is AB. So that element is say X inverse. Here A belongs H, B belongs K. Okay. Here that element is here applying the inverse is there. On both sides you are taking the one of the inverse is there. X inverse whole inverse is X and AB whole inverse. Now in the simple properties of groups, AB whole inverse means B inverse A inverse is there. So B inverse B belongs to K means inverse element is also same given the subgroup, and A inverse is also belongs to H is there. Every element in irrespective of the subgroups and their inverse element is also there. Therefore, X belongs to KH. Same element X inverse belongs to HK and X belongs to KH is there. Therefore, HK is contained are equal to KH. In the above theorem also, union of any subgroups is a subgroup if and only for one is contained in the other. Therefore, HK contained are equal to KH. The same element is also in the X and the element is also X. KH is there. Therefore, HK contained are equal to KH. Similarly, we can prove that KH is also contained are equal to HK. Okay. Therefore, A contained are equal to B, B contained are equal to A equals to B is there. Okay. Now, the sufficient part, converse part is HK equal to KH. Okay. Now, here HK is a subgroup of G means, first of all, HK is in HKB in a non-empty set. That non-empty set, we are taking any two elements X and Y. Therefore, X equal to AB is there and Y equals to C. C belongs to H and D belongs to K. Therefore, AB belongs, what is that? Here X equal to AB. That is the one of the product of the element. Y is also another element, that is C belongs to H and D belongs to K. So Y equal to CD is there. Therefore, A comma C both elements are in H, B comma D both elements are in K is there. What about the condition of A comma C belongs to H means here according to that X and Y elements, what is the direct condition? X, Y inverse. Replacing X equals to AB, Y equal to C. Okay. A of CD whole inverse means D inverse C inverse. There is no doubt. Okay, D inverse C inverse. Just you have to write this one. Now A of BD inverse of C inverse. See, this value is D inverse C inverse. BD inverse is one of the element, and C inverse is also taking at right side. Taking at right side. Now, that's why XY inverse belongs, according to the A belongs to, enter this element represented as KH. K is also belongs to BD, K is also equal to BD inverse, that is BD inverse belongs to K. This is also KB a subgroup. Now, just like nothing but like AB inverse belongs to H. And C belongs to H and C inverse belongs to H. Therefore, this element represented as KH. Okay, AKH. So XY inverse belongs A of HK because KH equal to HK is there. That is the given part. Finally, XY inverse belongs HK because A belongs H means AH equal to H is there. Okay, this is the left coset. Subgroup of the elements at left side, that is the left cosets of the element. Subgroup of the element at right side, that is the right cosets. AH is the left coset of a subgroup, that is must be a subgroup is there. Therefore, AHK equal to, therefore, according to this one, this is A belongs H, AH equal to H. AHK equal to same HK because HK is a subgroup of capital G is there. That's enough. This theorem is very important. And this is the simple corollary. This is also very important. This is the end of this session. According to the corollary, if H and K are subgroups of an abelian group of G, suppose G be an abelian group, there are two subgroups are H and K are two subgroups. Okay. What is that? HK is a subgroup of G. What is the proof? This is the simple short answer. H and K. Because in the multiple choice or fill in the blanks, whatever it is. Suppose G be an abelian group, H and K are two subgroups. What is the HK? That is the subgroup of G. Okay. Okay, HK are two subgroup of G. HK is a subgroup of G means HK equal to KH. Suppose this is the abelian condition. AB equal to BI is there. So by the subgroup of the abelian part, the abelian of the subgroup is also abelian. Therefore, HK equal to KH. G is abelian means we have HK equal to KH. Automatically, KH is a subgroup of HK is a subgroup of G because by this condition, HK is a subgroup of G. When the group it must be abelian. Okay. So that's enough. This is very important. Tomorrow we will discuss the cyclic groups and already we have to begin this one. Just you have to see here this theorem. What is that? This theorem is there. Just you have to see here. Okay. H and K are two subgroups of a group G. This is our PDF part. This is also one of the important theorem because today very important concept delivered here through me. Okay. Now there is no doubt. Today's important session because those theorems are very important theorems and well established in algebraic concept, especially in group theory part. And according to this one, we will discuss the rings and fields concept also. Okay. Now here the concept is H and K are two subgroups of a group capital G. Then product of the subgroup is a subgroup. If and only if HK equal to KH is there. Already we have explained. Just you have to recently. Okay, this theorem is just you have to see and refer. And this is also one of the proof. Okay, just you have to see here. H and K. Already one method is there. This is the another method. HK equal to KH. HK is a subgroup of G. Sufficiently, A is the HK, B is the HK whole inverse. H into HK into this is the sum X. This is the Y. XY inverse equal to HK into HK inverse.